All right. Thank you for coming. Today we want to report a little bit about a project what we had together where we evaluated a global load balancing use case. So basically our target was we want to build up like an infrastructure layer that we can behind host stateless services to be available on different clouds or different data centers. In direct, we was hosting it on AWS, Azure, and on-premise OpenStack environment, and want to have it reachable over one DNS name or one global entry. So, from my side, I'm working for Kubermatic as a principal architect, supporting customers since multiple years, and working with containers already 10 years. And then handing over to Nico.
Hi, I'm Nico. I work at DATEV in Germany, and I'm a cloud platform engineer, mostly working on our internal Kubernetes platforms.
All right. So what first, maybe a few things about load balancing. So the basics. So who is aware about load balancing in a bigger picture, who worked with this in projects? Are there some? Okay, not too much people. I expected more, to be honest. But yeah, normally everybody says, oh, load balancing, no. But really working with it is often not as common because you're getting often it provided from a platform. If you're on a cloud, you just say, hey, service type, load balancer, and here we go. But if you are on premise, maybe it's getting already a little bit tricky. So what is the target of a load balancer? Basically, you have several users, and you have one machine. It could be a physical machine or it could be VMs where you're load balancing the traffic to different servers. So servers are basically independent from each other but serving different requests, and there you have different strategies how you get served the request to it. Next, in Kubernetes itself, you also have load balancing. A lot of people know the service type, normal service type is cluster. So basically here, you deploy your application, you have a deployment, then you get a replica set, and you have n replicas of pods. They have own each IPs. And inside of this cluster, basically it's mostly a namespace, you have a service created, and this service then is reachable inside of the cluster. And this basically gives you a stable IP or a stable DNS name inside of your namespace to reach basically your pods. And then you can add something like an ingress spec. I think most of people know ingress specs. So it's basically giving you then something like, okay, that's the DNS name. Maybe I want to create a TLS certificate around, and basically then my application get reachable. But this is still inside a namespace or inside your cluster. But how you came to something outside, so the traffic must come into your cluster. And that's basically the load balancers. And you can create such things also inside of Kubernetes with the service type load balancer. But what happens then? Normally, I think 99% of the clusters have an ingress for layer 7 traffic. If you want to have layer 4 traffic, that means plain TCP, UDP, you need basically a service type load balancer. And this one is mostly in front of an ingress. And this creates then on the external side of your cluster a load balancer. So it's every time external. You basically say here a component what called cloud controller manager observe the object of service type load balancer says, okay, that's my backends, and the backends are node ports. So they go, if you take a look in the Kubernetes node, you see the node ports open now after you open the service type load balancer. And then the load balancer basically getting the IP of the nodes to the target node ports and forwarding the traffic maybe to your ingress nginx. And here you know then, hey, that's my app.example.com, so the traffic gets forwarded then to the service, and the service knows what ports can be reached. So that's basically how a normal Kubernetes cluster works. Maybe there are different solutions, but it's like the 90% use case, I would say. So what is load balancing about is we want to distribute traffic, for sure. But we want to also preventing overloading of backends. So basically that we don't say, hey, my backends go down, I can limit requests or I can do other filters. What is often important is health check. So check your load balancer implementation if they're supporting health check, because not all are doing it. So health checks means if a backend fails, in this case it would be the node of a cluster fails, is not reachable anymore, it needs to get moved away from the load balancer. And that's basically a pre-requirement if you want to go really in something like a high availability service or zero downtime deployments. Without load balancers, you cannot implement such things really easy, because if some pod or something goes down or you want to update, you need to switch. And this switching is basically abstracted by a load balancer in front of. Also, in kind of network security design, it's often protecting the backends so that you don't have access outside of your VLAN or your private network. It's the only way out, way in is the load balancer, and this is protected by firewalls and WAFs. So what is the difference between firewalls and web application firewalls? Normal firewalls just do TCP, UDP, IP port mapping, and WAFs are mostly doing layer 7 inspection and see, okay, what is the traffic about? So see headers and checking something like that. Okay, but keep in mind also load balancer is a single point of failure, because every traffic that reaches my applications goes through this component. So it's critical, and we need to be careful what we choose there, and especially on the on-premise world, it's maybe not so easy to get things. Okay, how this looks like on an on-premise data center. Basically, you have not just one Kubernetes cluster, you maybe have multiple ones. And they communicate to each other, and basically, let's say we have 2 clusters, and they have inner communication node to node. That's basically the east-west traffic. And then you need to get workload to your cluster. Basically, you're starting here, you have maybe a client going over the internet, then you have something like a FortiGate router where it comes in, and there maybe behind the scenes you have a load balancer, and the load balancer then forwards it to different switches where the nodes are behind it. For sure, there's maybe a layer of virtualized network in between something, but for simplicity, we keep it out. And then basically you serve hitting the node port goes to your service, and then reaching the container. And just the way up, we call it north-south bound. So, and this is basically what we want to talk about. And why a load balancer on the data center is not enough. Because of exactly this one, like OVH had a major incident where a whole data center burned down. I mean, it must not be like that, but if you are also in the hyperscalers, you get sometimes, okay, availability zones are down, okay, that's maybe you can handle, but sometimes it also happens on their side that the whole data center is not reachable. I mean, if you're hosting your own data center, it could be likely that a digger cut a cable or something like that happens, or you have a full electricity outage over multiple days, you are basically not reachable. So, but when do I need it? I mean, well, it depends. Everything costs money, and it must be a business case behind it. So if you just say, hey, I'm pretty cool in this tech stuff and I want to do it, you can do it, but it costs you. And normally business cases are, maybe you are forced to by regulations. So for example, banking applications, banking payment services need to be like fulfilling that they have multiple data centers approaches, or something like, let's say you're building a web shop and you have multiple locations like Europe, USA, Australia or something like that, and you want to have it reachable over one DNS entry, and this is basically where you say, okay, I need something around it, and that's the global load balancers. Okay, and in the target of the project, we want to see what options we have, and the first thing we came across was cluster mesh. So cluster mesh is basically connecting different Kubernetes clusters and then making it high available. So basically this was the first idea. So we placed one cluster in AWS, one in Azure, and one in the OpenStack DC. Then what is cluster mesh? So don't see it with service mesh. So service mesh is basically around service functionality and so on. Cluster mesh is more connecting two clusters together to achieve pod-to-pod communication. So basically you could, if you is allowed by rules, you can have here a pod what can then communicate with a pod there. That's basically what you reach with a cluster mesh. And you can there define some kind of global services. Then basically you have here a service, and this can serve traffic from this pod of this site. How they connect is basically you need a direct layer 4 connectivity between the nodes. So this is one thing what is keep in mind. So cluster mesh is not like building a tunnel or something like that. You need basically node-to-node connection. And then you have an extended cluster mesh API server where you basically are connecting to each other and say, hey, I'm cluster A, and here I'm cluster B, and they get connected. How it looks in detail, we will see later. And then basically the cluster mesh is able to create resources, to manage resources in the vice versa cluster. So, and basically so they handle it out that one service can distribute workload to another service by routing. I mean, eBPF experts are around here, so don't ask me. The target is to make it reachable. Yes, so that's basically it. The cluster mesh API server is normally exposed by a type node port or load balancer. Why? To be accessible outside of your cluster. So it must be outside of your cluster and talk to each other. Now, how we set it up. Basically, we set it up multiple clusters, and then we basically added the Cilium CNI, where basically Cilium brings this capability already with it, and you can modify it in the way to get it running. You find the code on the GitHub. It's not published right now, but we will do it after the event, and then you can see the configurations and so on, how we set it up. So first step, bootstrapping. So basically 2 clusters, and then you need kind of a network connectivity between them. You can use a WireGuard network, you can use VPN or side-to-side, it doesn't matter. At least the only thing what you need is really a layer 4, and it's important, means TCP and UDP traffic between the nodes. And then first step is you need to ensure that the CIDRs doesn't match. So the node CIDRs of cluster A and cluster B does not be the same. Normally, if you're creating like 5 clusters on a hypervisor or other Kubernetes, you see that the node CIDR internally for the pods have the same pod IP. So if you have cluster A, the pod can have the same IP as in the cluster B. To avoid this and to make the pod-to-pod communication workable, you need different CIDR locations. What you basically, it's nice, it's just a configuration in the IPAM, so in the IP pool, where you can say basically, okay, give me this part, step 1 or step 0, basically, before you're starting even with the cluster mesh setup. Then, first step is in the first cluster, you need to get the cluster mesh API server up and running. So you're creating that by a configuration, and then you get a service type load balancer for the API and a pod what is cluster mesh API. So this one is basically the config for it. So you say, okay, I'm basically cluster 1. I want to get exposed over a load balancer, and I get these annotations because I wanted to have an NLP in AWS. I added these annotations, and then I say TLS auto method, so then it creates certificates. There are for sure multiple ways to set this up, this handshake and so on, just showing you one way. If you need more, go to the Cilium guys and ask them in detail, and that's mostly how deep are we going here. Then, second step is, now we have the cluster mesh here running. The second step is that this Cilium daemon set ports need to talk to the cluster mesh API of cluster 1. And then we need to configure this one. So basically it looks the same, plus cluster ID 2, service type load balancer to also exposing a load balancer on my cluster 2. And then we're adding here, first step is the CA of the cluster 1. So we're copying the details over. There is a one command you're getting printed out, and there's a secret, and then you're copying it over. And then basically they can at least share the CA. Next step is that you need to basically configure the connection. You say, please connect to cluster 1 in this port and this IP. Here, because I'm falling into this trap, you need to really get the IPs here. And this must be a stable IP. Not CNAME, does not work. It's IP. And then basically for authentication, you're adding the TLS cert and key. And then basically this cluster 2 can now talk to the cluster mesh 1 API server. Next step, step 3, is the vice versa from cluster 1 to cluster 2. So basically also saying, hey, this way connection is also possible. This is then the last step. So basically in cluster 1, we configure the same CA, and then cluster 2, the certificates of the cluster 2 copied to it, and the IP also from the cluster 2 load balancer. Sound complex? I must say it's also complex. You can do a lot of things wrong with copy pasting and so on. So you find it also in our documentation, but this is basically how the bootstrapping works. So what then we achieved is basically we have then a connection between, and then I can really talk pod-to-pod communication and can then build services around. So there's also a health check where you can see, okay, here's connections, say testing all nodes to each other if everything is okay and if the connection is fine, and if you're fine, you can go next, and then building like routing strategies. So basically, what is cool, you just need to add some annotation and say global service, and then you're giving some strategies, and on the left side you see some different strategies. Basically, you can say, okay, I want to just have a local failover, so it means, hey, I have a service here and I want to reach this port, or not other way around, so you need to see from the direction where you're applying the service to make it sensible. And then you can make, what we choose mostly was then we say local first. So if you are reachable, then use the local one. If it fails the local one, go to the remote one. And this you do vice versa, and then you basically are reachable. So what happens then in our case? So basically our case was not really to have workload inside of the cluster fail over. We want to have really a data center outage scenario. In this case, we have here two services, what are basically DC1 and DC2, and maybe you have a DNS entry on top of it, what is app.example.com, where basically points to these two CNAMEs. And then you have the front end, traditional service, back end to the back end ports. Then on the DC failure, first, we simulated basically that here the pods are failing, the failover works great, and the backend pods here get addressed also from this side. So basically the traffic get here into this ingress and then basically get forwarded to this side. But then we shut it down the complete worker nodes, and then also the cluster API server, cluster mesh API server was down. And then basically the problem is this is not a covering case. So there we find that this basically is not functional anymore. So basically if someone hits then DC2, he does get nothing back. And that was for us the reason to go further and go to the next step, what is now Nico is explaining, what is then a global status load balancing.
So basically we start with one idea. What if we treated the whole world as our one availability zone? No more telling users to hit traffic in either one of those data centers or treating even data centers as single units, but stretching. Well, the first option, as always, is just Google Global Service Load Balancing and pay your favorite cloud provider or CDN provider. They all have offerings, but we are techies, we like to build stuff. To be completely honest, I wouldn't recommend building this solution I'm going to show you alone, if you're the only one that will be on call, but it's a pretty cool solution. So, not unlike your last incident during on-call, the solution is DNS, because it's almost always DNS. And quick reminder, I think everyone knows how DNS works. We basically go ahead, our client asks the DNS system, hey, where's example.com, DNS answers, and now we know which server we have to talk to. It's only built because humans don't like numbers, we like names. Pretty simple. Then there's an option we could maybe expand it a little bit. So same basic principle, we ask the DNS, hey, how is stuff going? Where's example.com? And we combine our classic DNS server, which is pretty much a stupid text file, with some kind of health check logic. So our DNS server has some health checks and asks the servers, hey, are you healthy? In our example, the first server, not very healthy, it's currently burning, so the DNS server automatically only answers with the IP address for the healthy server, and we connect to the healthy server. This is the entire baseline idea. It's not that complicated. Implementing it can be complicated, but there's always a CNCF project that comes to the rescue. In our case, it's KHAB. It's the Kubernetes native global service load balancing solution. And it handles all of those DNS and health check things for us. The basic ideas, we have KHAB. KHAB includes its own DNS server, Core DNS, probably all know Core DNS. And Core DNS handles all of the, okay, you can find the website at this address. It also includes another CNCF project, external DNS. This is used to tell our upstream DNS server, hey, please look at this core DNS for this subzone. So if you all remember, DNS basically is just a bunch of zones, starting at the top level domain, then our second level domain, example.com, third level domain, app.example.com, and so on. And for every level of this domain, another server could answer the question, where is it actually? To know how to set the right records, KGB just looks out for ingresses and services related to ingresses. You can also manually configure it, but it's the simplest way. So you just tell it, hey, look over there, that's my ingress for example.com. Please create a DNS record. But one instance of core DNS isn't really global, so like Toby said, we started with a couple of clusters. For this demo, we choose a Kubermatic cluster, a GCP cluster, and a cluster from DATEV. And they are all configured exactly the same. Well, kind of exactly the same. But the main thing is there's KGB running on all those, the same stateless echo service is running on all those, and the same core DNS included. So like we said, we just add our upstream DNS. So KGB handles telling the upstream DNS server, we just used Cloudflare, to redirect all questions regarding where is our example app to the core DNS servers. And by default, it just tells them, hey, look at one of those 3 servers. So most clients will just round robin and ask the first server, the next server. They will handle it. One of the servers will probably always answer. But right now, these core DNS servers here can only tell you about their own IPs. So we need some additional communication. This is also handled by KGB. So basically, the KGB in cluster 1 checks the core DNS in cluster 2 and asks, hey, which records are available? That does the same for cluster 3 and so on. So we had our user. The user just goes to DNS. DNS tells him, hey, please ask the first cluster. And the cluster says, hey, go to DATEV. Pretty simple. Let's try it out. And I really, really hope the demo gods are on my side still. Yeah, of course they aren't. Why wouldn't they be? There they are. Nice. So setup is pretty simple for KGB. It's a Helm chart. You just install it, provide some basic values. The values are pretty simple. You just tell them, hey, I'm cluster 1. These are my friends, cluster 2 and 3, and we all serve DNS for a specific domain. In our case, the top level domain we chose, or the DNS edge zone it's called, it's nig.gl, one of my domains. And we tell it, hey, don't serve traffic for all of nig.gl, only serve traffic for everything that comes after KGB nig.gl. And to make things a bit faster, we tell it, hey, to communicate across each other, please look at the upstream DNS. There are some additional settings for Cloudflare, because I use Cloudflare as DNS, and for AWS, because the standard AWS load balancers don't support UDP. By the way, your load balancers have to support UDP. That's one fun fact. And then we just deploy the typical dumb echo service, just answers hello from, and then a name, and nothing special here, just the normal ingress, nothing configured. On the right side, you can currently see, hey, these are the answers I get when I call dig for demo KGB NICGL, and the answer when I curl it just runs a botch. These are the pods in my primary cluster, and these are the nodes in my primary cluster. They will come in handy soon. So let's start with the basic example as failover. This is currently happening, so we say my primary target is cluster 1. But we can also go ahead and switch to round robin. So this will just apply the same config to all clusters. The config is pretty simple. Please look at this ingress resource to get the IP and DNS, and use the strategy round robin. You can even do weighted round robin, so not only will it answer 30% this, 30%, 30% over there, but you can set it. It isn't magical. If you query it 10 times, you might get the right response distribution. If you query it over 1,000 times, you definitely will. So this is pretty simple. We get pretty much randomly answers from cluster, but this isn't the more destructive use case. So let's destroy some shit. So I just set it back to primary. By the way, to set stuff to primary, you just say failover and primary. This is all it takes. And let's stop our service. in cluster 1. Let's just scale it to 0 replicas. You can see the replicas are started dying, and there we have it. Cluster 1 is obviously down. It will take a couple of seconds. You can configure that because a lot of DNS queries will potentially get a rough message from your admins. And let's see, and pray a bit to the gods, that it will actually fail over, because that's the one thing about DNS. DNS likes to cache on the client. Hey, there we are. Failed over to cluster 2, and if we switch it over again, everything will be fine. There's a longer version of this demo in the GitHub, but I think we don't really have time for that. So let's switch over to the lessons learned. As we saw, cluster mesh is pretty cool if you want to do some fine-grained traffic management, MTLS, pod-to-pod communication across data centers and all that, but it fails as soon as you want to do a real failover where one of the clusters just goes ahead and dies. On the other hand, global load balancing, DNS, it's a core technology. It has always worked. It will probably always work. You can just manually overwrite stuff in your DNS if you don't trust it. And you don't need any kind of node-of-node communication. Only the DNS servers have to talk to each other. On the other hand side, you don't have any traffic management across ports. And DNS, TTL caching on some clients can be a real bitch. It happened to me before. It probably happened to everyone before. That's the part of it always being DNS. And you can combine them, of course. Good luck with that. We tried it. It works. It's awesome, but it's a bunch of work. And you can also use some of these nice CNCF projects to schedule stuff across clusters. We had a talk yesterday, and there will be another talk today, I think. So you can say, hey, only schedule my workload in cluster 2 if cluster 1 is full and I can't scale the nodes anymore. Stuff like that. And with that, thank you very much. We will share the slides and code afterwards.
So, how many of you knew about K8GB before this talk? Pretty less. Okay. Great talk.
Thank you. Great talk. I will definitely try it out because I do run into these problems all the time. So my first question is, usually I do very similar things with just Cloudflare. You know, they can do this on a global scale, poll the regions, and then, you know, like route the users to the closest, you know, healthy endpoint. And then, you know, a couple other things can do the same, like Azure Traffic Manager, I believe we also use that. So can you compare that, you know, this solution to those? And this is the first question. The other one is that we do use, there are like global load balancers on the same cloud, like I think AWS Traffic Accelerator. You do get like one IP for all of the regions, although that's, you know, like one specific to those that provider, so you cannot use multi-cloud and stuff. And then everything happens in the same, you know, like cloud provider. So can you do just a comparison in this?
Sure.
Yeah, the quick answer is pretty much it's the way of buying a solution or building it yourself, because, of course, Cloudflare does the same stuff. This isn't a new invention by KGB. This wasn't a new invention by Cloudflare. It's pretty much a question of, do you want to offload it, or do you want to do it yourself? And it's the same for the global load balancers provided by your favorite cloud provider. You have to trust your favorite cloud provider. And my company, for example, has some finance regulation stuff where we are not allowed to deploy the full workload to one cloud provider. So we have to do some DNS-based stuff because one IP address would also always be related to one cloud provider.
Maybe one addition. What I like there, it's basically simple DNS. So if something fails, you still can override DNS entries and you get away from it. So you basically don't rely on the global service of a hyperscaler or something like that. Basically, it's a DNS entry where you rely on. And if the DNS is something what you can easily fix, because it's just like, okay, now update the record to something else, I think you are much quicker up in this disaster case. And for me, it was like that, thinking about data center is down. You don't care if the service switch over takes 10 seconds or 1 minute or 20 minutes because your data center is down. But what you care is maybe you don't want to debug hard stuff. DNS is simple. You can just override and say, If it's not working, KHP, okay, keep it out of the picture, overwrite the DNS record. And that's what I liked. And I think also from the use case, if you maybe have not this budget for paying such global load balancers, it's also cool for kind of edge setups where you have small clusters somewhere. Basically, you just need a DNS server as external dependency. And that's basically works really stable. So we tested it quite heavily, so it was every time stable, and it's not as complex. And also shout out to the KHGP maintainers, the documentation is great, so it's also working right off the box how they described it. And I also think implementations, for example, F5 are implementing that in the same way.
You mentioned that the project uses external DNS. Do you have to deploy it on your own, or is it in the same Helm chart? Or?
It's just deployed via the KGP Helm chart, and they only use external DNS in order to support the wide range of upstream DNS providers. They have a built-in support for info blocks, but for example, Cloudflare, why build your own logic to tell Cloudflare to create a new NS record if you can just use external DNS?
And you can also inject those external DNS plugins, or do you?
Yes, you can.
Okay.
You can also choose to not install external DNS together with KHGP and run your own.
Okay, thank you.
Okay, last question.
Thanks for the talk, that was great. With KGB, can you do geographic load balancing? So can you say there are these clusters available, and if I'm in Europe, I go to the closest one in Europe. If I'm North America, I go to the North American one.
Well, by default, the configuration itself doesn't allow it, but because it's just using core DNS under the hood, you can use the core DNS plugins for geographical resolving of IP addresses.
So you basically need to add their a database, basically where...
The good old MaxMind GeoDB database, I think everyone who's ever had to do stuff like that knows it. And then you can do it, but not by default. You have to do a little bit of work.
But it's also not too hard.
Not too hard, yeah, not too hard.
Not be scared.
Thank you, guys. A round of applause.
Thanks.